Hello, everyone. My name is Dan Jonas Roach, and I am the news editor here at the Architects newspaper. I'd like to welcome you all to the Enhancing Indoor Environments with Mixed Mode Ventilation live webinar, a CE Strong webinar series powered by the Architects newspaper. This webinar is sponsored by Window Master. This program is registered with the AIA CES for continuing professional education. Questions related to specific materials, methods, and services will be addressed at the conclusion of this presentation. This webinar is recorded and can be easily replayed when re-registered on the same webinar registration page. Please allow 7 business days to process certificate of participation and AIA credit reporting for this presentation. At the end of this course, participants will learn about wealth and wellness benefits, i.e. learning how mixed mode ventilation systems improve indoor air quality and support the physical and mental well-being of building occupants, thermal comfort with mixed mode ventilation, discover how a mixed mode approach can enhance thermal comfort and energy efficiency across diverse building types, control strategies comparison, understand the differences between automated control systems and manual override strategies in maintaining optimal air quality and comfort in mixed mode systems, and real-life reference cases. Gain insight to how others have utilized these powerful strategies and relate to building projects across North America. We encourage you to ask questions using the Zoom Q&A button found at the bottom of your Zoom window. Now, I'd like to introduce you to today's presenters, Michael Sullivan and Casper Homark Reven. Michael is the Business Development Manager for Window Master's West Coast Territories. He has been a part of the glazing industry for over 17 years while in Minnesota. Recently, Michael moved to Los Angeles to join the Window Master North America team, bringing his expertise in project management, facade design, and glazing knowledge. Casper is a building performance engineer at Window Master and part of their Ventilation Institute. He plays a key role in the natural and mixed mode ventilation strategies of Window Master in Europe and North America, including building performance simulations, life cycle analysis, and building codes and standards. His area of expertise is to support the stakeholders of building projects, such as consulting engineers and architects, to achieve successful passive ventilation designs with a focus on sustainable solutions and wellness of building users. Casper has a master's in science and civil engineering from the Technical University of Denmark, specializing in the indoor environment, HVAC, and sustainable design. Remember to please leave your questions for Michael and Casper in the Q&A window. And without further ado, here's Casper.
Thank you, Dan. So my screen is sharing now, I assume?
Yes, please.
Yes, perfect. Okay, for today's agenda, we have a combination of concepts and studies with more practical information. So I'm going to talk about wellness and thermal comfort, while Michael will address more practical details about the actuator hardware for windows, design, mounting, and features, and also talking about what goes actually into an automated natural ventilation systems with the components and so on. Now, natural ventilation really starts with the architecture. Personally, I think it's the most important aspect for a successful natural ventilation design. It really impacts the fresh air that we are able to bring into our buildings, but it's not just about the ventilation, it's also about the overall thermal comfort of the building, where the entire design with glass area, solar shading, building mass, and so on plays a huge role. Through the recent years, we have had or been relying a lot on mechanical cooling components to achieve good thermal comfort in our buildings. But this is not necessarily the best way to always do it for the comfort of the occupants, and it's not always the best thing for a sustainable approach. Before we had mechanical cooling. It was really the designer's job to utilize the building design and the features of the building itself to achieve a good thermal comfort. And I think it's extremely important that the architects are a central part in the communication around thermal comfort and wellness, and can help really communicate these concepts to the building developer from the very beginning. My favorite projects are the ones where we have really good communication with the architects and maybe the building owner, and are able to get these concepts of passive ventilation into the design early on. The project showed on this slide here is a kind of a modern take on a Viking hall designed by Henning Larsen. It's the clubhouse of the Scandinavian golf course, a little bit outside of Copenhagen in Denmark. And as you can see, they have really tried to play with these old design concepts for passive features for solar shading and natural ventilation and so on. With natural ventilation and wellness, we are often talking about this access to the natural environment, because different studies have shown the great benefits of locating building users closer to the facade. So both in terms of natural ventilation, of course, but also daylights and window views. This has shown to really increase productivity and reduce what we call the sick building syndrome, which is a term that covers health and wellness in buildings pretty well. It's about all the common issues that we experience in building, such as concentration issues, getting tired, headaches, dry eyes, and so on. One of the great benefits with natural ventilation and operable windows is that we're able to bring the fresh air directly from the outdoors into the building. This ensures that it's not going to be polluted by any dirt or dust before reaching the occupants. One of the studies about the sick building syndromes has been made in classrooms. This study really shows the positive impact of natural ventilation on the prevalence of the sick building syndromes. And one of the findings from this study was really that it's often caused by insufficient cleaning or maintenance of the HVAC system. So the air delivered to the occupants can be polluted by bacteria and dust. This is something that will, of course, vary from project to project. But I think that there is probably a lot of buildings out there where the maintenance and cleaning of the HVAC systems are not done properly. We know that this can already happen after 2 years from commissioning, that you see a buildup of dust and so on in the systems. One project to utilize natural ventilation very successfully in classrooms is the beautiful Kresge College, located in the Redwood Forest in Northern California. Here they utilize high-level windows to deliver fresh air to the occupants. One of the other benefits of operable windows and natural ventilation is that we are often a big portion of the year able to deliver air change rates beyond what is typically required in terms of the air quality. And this gives us the ability to make this kind of flush effect of the rooms, where we can quickly remove bad odors or chemicals from materials. And it can also be be beneficial in periods with high infections numbers, that again, we are able to quickly remove the old air from the indoor space. And with that, I will give the word to Michael. If you're ready, Michael.
I am ready. Thank you, sir.
Good.
So I will be covering kind of the basic hardware and solution design for automation and occupant comfort. As you can see here, we're going to start off with the window and vent types. The biggest portion of this is the window and vent types, so it's very important to know why they're significantly important to occupant comfort by enabling the indoor-outdoor climate, or the relationship between the indoor and outdoor climate, providing a more comfortable and controlled environment for the occupant inside, while also using the outdoor elements. These can be used for improving air quality and also psychological well-being. There are a few trade-offs to this, as there can be excessive wind, increased noise, and air leakage, but that is all within the basis of design at the beginning of the process. Our 24-volt DC actuators, these are the typical models we use within every project for natural ventilation. On the left, you see the chain actuator, the louver actuator, which is typically used for a pivot window, the locking actuator. I've typically seen the locking actuators on casement windows to help secure the windows. Usually that's more of an add-on actuator, but we have seen those used in products or projects. And the spindle actuator is typically used on heavier angled windows or skylights. So what is inside and how do the actuators work? As you can see in the picture here, they're sealed within a specific housing. It's either painted, powder coated, or anodized. And the key components within these chain actuators are the chain and the chain cartridge. And one tip to understand how it works is the longer the stroke and the heavier the window, the bigger the chain will get and the housing will suit, or for the housing to suit. So the bigger the window, the heavier the window, the bigger the actuator we're going to have. We have some pretty heavy ones that we call elephant actuators, and that's exactly why they're heavier and more heavy duty. Of course, we have the motor. Again, bigger the load, the more powerful the motor we will need. These are usually normally 24 volt, and we have had higher amp drawn on some other projects for heavier duty, but that's within the programming and maybe more of a custom order. And then as far as the electronics, many of the motors have the basic market feature. They have the motherboard, some wiring, and also now there is ways to go about waterproofing. Not 100% waterproofing, but it can help with waterproof in case you set these actuators in a greenhouse or the elements outside, and any water that gets on the chain will retract back into the motor. We do have steps to help with that. I don't want to say waterproof it entirely because that's not possible. And now getting into more of an aesthetic side, more of the design side of this, and how it can be aesthetically and visual pleasing, and also help with the well-being, where you're not staring at wires, things like that, just hanging all over the place. The first topic is the surface mounted and cover caps. And I have a little sentence here for each. There's the pros and cons. So surface mounting is going to be the most cost effective. It's time saving because what you'll be doing is you'll be mounting it with brackets to the surface of the window, and then the chain actuator bracket will just be mounted to the operable side, pushing and pulling that window back to seal and open. And typically with these, most actuators are delivered natural anodized aluminum, but in the market now, I have the RAL numbers. So these models come in gray, dark bronze, white, and black. We can do custom colors. Of course, that's not going to be as cost effective. With the negative portion of the surface mounted, there's the visual aesthetic. It looks more mechanical, and you're looking at all the bells and whistles that go into this system, unless you move over and start to do something with a cover cap, which I do recommend. With my glazing background, it always makes it look a lot nicer. If you look at the picture on the far right, that is with the cover cap. And then the one to the left of that is the actuators that are sitting behind that cover cap. Typically, that's going to be a piece of brake metal, or if we can get in touch with the window manufacturer in the first steps of the project, we can help design. But again, that's going to be on the glazers and the design team to figure that out. As a actuator provider or manufacturer, we don't provide those angles, but we can help and assist with the design phase. Another point for the cover cap for the actuator is that you can color match. So you could go with the baseline color, which is gray or anodized, and have that covered under a cover cap that matches and is flawless with the system. So you don't have to worry about the cost of custom color or actually seeing the wires, anything like that. And it's also very easy to remove for future maintenance, unlike our next slide here, which is the concealed application. Now, again, this is a great application because the aesthetics, and you can keep it out of the reach of occupants, so no one can fiddle with wires when they're not supposed to, or small children getting their hands on the motors, things like that. But the biggest concern with concealed is the future maintenance and troubleshooting. From what I've experienced with a few projects in my past, were that you'd have to take that whole bottom of that window out to get to the actuator. So it might be a little more manipulation and reconstructing of the window after you replace or troubleshoot the actuator, as it's basically going through the frames and concealing from the maintenance crew or the installers. So one thing with the concealed actuators, or just the regular surface mount, is a big topic that's been coming up lately is the vent prep for cabling. As you can see here, one of our recommendations is to have 3 core flex to control the local connections and the junction box. There's some grommets to protect the flex at the top. And one recommendation is to really clean out once you drill into the window sills or the mullions, is to watch for burrs that can damage that cable flex. Because once they're put through, there's no way of knowing until you pull all the cabling out to see if that's going to work correctly. We also recommend using clips or some kind of containment, maybe a conduit of some sort, to make it, again, aesthetically pleasing, and so people aren't picking at the wires and then not being able to use the actuators because the wires are malfunctioning. Now, as far as how this all works, am I getting ahead here, Casper? I just wanted to make sure if I'm ahead here.
No,
Okay.
it's perfect. No, you sure, Michael.
So one of the technologies that can help with sustaining the system and communicating throughout the entire project to make these concepts happen for thermal comfort and manual and automated control is the motor link technology. It's a unique two-way communication between the actuator, motor controller, and the BMS system. So with this, the motor controller is kind of the center for all of this. And that's where all of the features come in with position control and feedback. There's a 3-speed operation system where it also produces sound level differences with those 3 speeds. The faster it gets, the louder it gets. But if you're at the lowest speed, it's almost silent. You can hear the seals break on the windows, but it's almost entirely silent. There's a reversing function and the genuine synchronization between all motors within that control panel and the BMS system. And to have that done, it's usually done through an open bus communication, which is typically BACnet, KNX, LON, and Modbus from the BMS system, which then you can find more parameters within the BMS system to control when the window's open, what zone is opening, what zone should be closed, and all of those parameters. Now, a simple connection diagram for this is as shown. You have the synchronized dynamic facades, the movement and control across the opening and closing of the highest level. You also have the safe operation with the closed mode. The window actuators can detect obstacles, preventing the operation of closing. So there is a pinch point. I have tested that pinch point by accident. So it does pinch your fingers, but it won't break, but it will back off at a point to where I can't push this in any further. We need to back off and start maybe a trickle effect or wait a couple minutes to close again. The accurate control and feedback, which is also presented from the actuator, sending the signal back to the motor controller saying this zone on this window is having an error, and then that can be communicated between the controllers and the BMS system. And again, the whisper quiet operations is the 3-speed. It's actually called true speed with the MotorLink technology, where you can have it to almost silent. It's a little whisper, but it's not affecting the people, the occupants within the building with loud grinding, anything like that, if the installation is done correctly. And with that, I am going to pass it back to you, Casper.
Thank you, Michael. So I think there was a bit confusion with the screens before. Sorry about that, but I hope it works now. Yeah. So so now I'll talk a bit about natural ventilation and thermal comfort. I know when people think about natural ventilation, it's often in relation to sustainability or reducing energy consumption. But how we do that is often related to thermal comfort, because thermal comfort dictates how much we can utilize natural ventilation throughout the year, and therefore how much energy we can save. So what is thermal comfort? A lot of it is perception to a high degree. It consists both of physical and psychological factors. We of course have the temperatures, where the operative temperature is most commonly the determining factor, and this can be defined in different ways, but most often it's an average of the air temperature and radiant temperature, and I'll talk about a little bit about that later in the presentation. But we also have more indirect factors, which many don't necessarily think about in the beginning. Something as the design of the environment can impact thermal comfort. The air quality, if the air is stale and stuffy, it can make the spaces feel hotter. And lighting and acoustics can also impact thermal comfort. We also see that people have a tendency to adapt based on the year. So the natural thermal comfort level will be lower in the winter time than in the summertime. What I really try to illustrate with this slide is the fact that there's so many different factors that goes into thermal comfort and varies from person to person. Yet we are often trying to dictate as designers what good comfort is in buildings. And what we should maybe talk about instead is creating good conditions for thermal comfort, but still provide the building users with some agency of choosing when they are comfortable. A survey database from the Center of Built Environment at Berkeley have shown the most common reasons for dissatisfaction in the built environment. And the most common factors we can see are all really related to a lack of personal control or perception of control in our buildings. And one finding was that people with access to thermostats or operable windows were in general more satisfied with the temperature inside the spaces. When we're trying to dictate what thermal comfort is, the expectations of the users are also much higher. One project that really takes advantage of these benefits of providing personal control is the Baltimore School of Law. As you can see, it's a pretty large building. Therefore, they have to use this central atrium of the building to exhaust the air and pull the fresh air through the facade. Now, the facade windows in this building are mainly manually controlled. And this is because there was a lot of focus on using operable windows and natural ventilation in this project as a feature for personal control to the occupants. Another study is showing a direct link between the satisfaction with the temperature and perceived control. We can see here from the results that natural ventilation has a great impact on people's satisfaction with the temperature compared to more traditional HVAC systems. And this is not necessarily depending on the actual temperature of the building, but what we can see on the graph to the right is that there is really a direct link to the perceived control that people have in this building. So again, when we're trying to dictate comfort, people will also expect near perfect conditions. Whereas if we provide them with control, there are more acceptance of a wider range of temperatures. A common building standard to address thermal comfort in buildings is ASHRAE 55. This specifies a comfort zone based on both physical and psychological factors. Some of these factors are metabolic rate, the clothing level, temperatures, airspeed, and humidity. And we're not just talking about a specific temperature here. It's a comfort zone that we can actually move up and down by manipulating some of these factors, especially the airspeed and radiant temperature. And it's also why the architecture, which I will show, is so important in terms of determining this comfort zone. But it's not in all buildings, especially with operable windows, where it's possible to comply with the standard comfort zone of ASHRAE 55. And therefore, another method called the adaptive comfort model has actually been adopted into ASHRAE. And this is to allow designers a greater flexibility to design buildings with operable windows with the goal of enhancing comfort and reducing energy consumption. This method was adopted into ASHRAE based on very extensive research done in 160 buildings on 4 continents in different climate zones. So it covers really a wider range of different scenarios. And what was found is that natural ventilation or the comfort temperature in buildings with natural ventilation strongly depends on the outdoor temperature. People, again, with operable windows and natural ventilation can accept and sometimes even prefer a wider range of temperatures. And this can be explained with preferences, psychological and behavioral adaptation. When we talk about natural ventilation, people will always often assume that natural ventilation cannot be used when the outdoor temperature exceeds our comfort level. And this is actually not always true. There are ways that we can manipulate the comfort on other factors than the temperature to achieve good comfort. One is the air movement inside the occupied space. As we can see from the graph to the left, which is also found in ASHRAE 55, we can actually manipulate the comfort zone by increasing the airspeed inside the space. And this can be done by several degrees. With personal control from, for example, operable windows, where the building users has some influence on the airspeed and the air movement, we are allowed to use higher airspeed to improve comfort. On the picture, the project shown on this slide is the visitor center at Minnevaska State Park Preserve. And this, as you can see, utilize these high-level windows for natural ventilation combined with ceiling fans to really optimize the comfort. We also see this in other projects. For example, the Chemeketa Community College in Oregon, where they have a similar approach of natural ventilation combined with ceiling fans. We also see this at the Pleasant Hill Library in California, where they have a big open space with possibility of cross ventilation from facade to facade, which is already great to create air movement inside the space. But they're also combining this with ceiling fans to really enhance the effect, especially in periods with more calm wind conditions. In connection to air movement, we also have to talk about night cooling or flushing, which is another very important topic with natural ventilation, and again, why the architecture is so important. I use both terms, cooling and flushing here, because there's really two goals with opening the windows during the nighttime or outside of occupied hours. One is to remove the excess heat from the past day, and the other is to cool down the building mass below the comfort temperature, and this is reducing the radiant temperature. And we talked about the operative temperature a little bit earlier, where it's an average of the radiant temperature and the air temperature. So if we reduce the radiant temperature, we can actually allow a higher air temperature inside the space and still have a good operative temperature. But what we also see from the results in projects is that by cooling down the building mass, as shown on this graph, you can actually keep a nice, comfortable indoor temperature at an acceptable level, as shown here, even on days where the outdoor temperature it gets pretty high. And this is due to the building mass and will vary from project to project, and why the architecture is so important, because these kind of results are only possible if we have a building that's really designed with the building mass, not having an excessive solar gain, using efficient solar shading, not having large glass facade oriented towards south. A project really utilizing these different strategies for thermal comfort is House Zero at Howard campus in Boston. This is a building that's part of a research project called Naturally, which is a collaboration with Snøhetta, Skanska, and Windowmaster. And this building utilized natural ventilation through the entire year, so both summer and winters, combined with a radiant slab system based on geothermal heat and cooling. It also has effective passive solar shading. This building is not the typical project. It's also a research facility where these different strategies can be tested every day. But since natural ventilation is used the entire year in House Zero, there's also been a lot of focus on thermal comfort, of course. And what the typical model we use to evaluate thermal comfort is the PMV model, which is the predicted mean vote of percentage dissatisfied users. And what a updated study of this method has shown is that natural ventilation doesn't really follow the prediction of this method. What we can see here is that when you evaluate the percentage of dissatisfied users based on perception of the indoor environment from cold to hot, we can see on the results here with the triangle for natural ventilation that people are much more accepting of warm and hot conditions with natural ventilation. And this is again directly linked to personal control and having agency of the indoor environment that the users are occupying for most of the days during the work week. Another beautiful project utilizing the concepts are Gullaug Torg in Oslo, in Norway. This project is, or this building is actually also a part of the naturally ventilated research project. But opposite to House Zero, it's not a research facility. It is a regular office building where there has been a big focus on reducing the operational complexity of the building. Here, naturally ventilated is also used through the entire year, but since Oslo and Norway is a northern country, there's been a lot of focus on thermal comfort during the winter, where it can get very cold, and different strategies have been engaged. One is using these high-level vents above the occupied zone to deliver fresh air in a very controlled manner to the building users. These here are not typical openings. We most often see windows used for natural ventilation, but here we needed vents with sound reducing features because of a river located outside of the building. These type of vents, as Michael also talked a little bit about before, is very commonly used for natural ventilation and often recommended because they are easy to control. They are away from the occupants in terms of safety, and they are very great to deliver fresh air to spaces during shoulder seasons or even winters. Here is the office plan or the floor plan of Gullaug Torg. And opposite to Baltimore School of Law that I showed before, we have a narrower floor plan, so we can here utilize just cross ventilation for the airflow. It's not necessary to have a large, yes, it's not necessary to have a large central atrium. You can see here the openings connected to the open office space. And during colder conditions, it's actually possible to open the windows or the vents in segments to have a more controlled supply of the airflow, where cross ventilation with air movement may not be as beneficial. There's also been a lot of focus in Gullaug Torg on user feedback. We use different strategies to optimize thermal comfort. We have what we call trickle ventilation, which is a very small opening, supplying a continuous airflow to the space. And then we have what we call pulse ventilation, which is a larger opening and a higher airflow, but for a limited period, such as 2-3 minutes. And we have tested these different strategies and received feedback. And what was found is that the building users, they prefer the more dynamic approach with the pulse ventilation. So even though they are supplied with a larger airflow of colder air, they still prefer this compared to the more continuous airflow. And this is actually also what we see throughout the last 30 years in many of our projects, that humans have very good reception of these more dynamic conditions. This kind of feedback also allow us to optimize the system based on the user's preferences. They are able to also give more detailed explanation of what they like and don't like. And I think this is something that should be more common in building projects. It does require a little bit of a budget, but it's a very minimal cost compared to the overall cost of the building. And I think the comfort and the wellness of the users should really be a very high priority. Before giving the word back to Michael, I want to just mention some tools created by the Center of Built Environment at Berkeley to evaluate the potential of natural ventilation. One is the thermal comfort tool, where you can actually see the comfort range based on different factors. And you can also see the adaptive comfort model here. Another is a climate tool, where you can actually on a map pick a weather data file and see the potential for natural ventilation based on that. We also have tools to evaluate air movement with fans and radiant temperature inside the space. So I think these tools are very great also for architects to use in relation to thermal comfort and wellness. And then I will give the word back to Michael.
Casper, did you just want to share your screen so we made it easier for everyone? And then
I can do that.
It's
just a couple of slides.
Yeah.
Yeah.
I don't have much else to say.
I'll do that. System design. Perfect.
Yes. So the system design is something to really consider when we want to achieve these goals. And a sufficient design is one that's shown in this slide. As you can see, it has all of the components and how they seamlessly work together to make the occupant comfort and occupant wellness and thermal comfort concept come together. I can start with the keypads, which are on the far right side next to the windows. Those are going to be the manual override switches for the occupants. And that was one thing that you really want to consider, being in the hands of the occupant to serve as their sense of control and self-comfort if they want the windows open or closed, or just to have some type of involvement in the occupant comfort. As you can see, in the middle, it has the intelligent door climate system, which is usually going to be the BMS and control panel system for actuators and all of the sensors. With that, we have the indoor temperature sensors, the CO2 sensors, and the humidity controls, which would typically be with the indoor temperature controls. And those you typically want to have near the windows, but also be able to read the entire room that they are based or zoned in. So you can have that indoor-outdoor comparison and where we need to regulate the levels. We also need the control panel, which is, I've had architects say this to me and also colleagues. It is a architect's nightmare on where to put the control panels. as you don't want the small power box out in the open to kind of take away from the aesthetics, but also you don't want them in the floor or in the ceilings to make it harder for the controls person or maintenance to go through and try and get to these panels. We have had the control panels in the floor and also in the ceiling on projects, and it can be quite nerve-wracking when you're on top of a ladder in the gutter, or not the gutters, but the ceiling, to try and get through to that control panel. With the control panel, again, it can be really regulated to an electrical closet, or with any other electronic control boxes off to a set area. As we move to the outside, we have the outdoor temperature, which is a rain and weather station. Typically, what you would like to do with those is have those at the top of the rooftop to control or communicate back the elements outside. Wind control, you just need it at a very sufficient space to where it's going to be hit with all elements, heat, air, and precipitation, to control back what sides need to be closed, or what's coming and how the system should react to those elements. So on the next slide, I have some of the components which are consisted within the system. There's additional hardware pieces as a USB stick, which can actually be used to fully automate the entire system and become a living, breathing building on its own, with just a simple dongle that you'd put into the control panel or the BMS system to read everything that is regulated, coordinated, and all the algorithms that are already set. So you go in, put that dongle in, and it can control the entire system on its own, with manual override as an option as well. And as you can see, this is one of the more, they're called plus panels. They have more ways to interact and integrate per zone, per window, per motor line. I would say per motor line over per window, to regulate how far they're going to open, or also show an open close or error message on where the window is at. In the middle here, the manual override switches, we do have the rocker switch, which is a simple open close. There is another switch in the market that is an open close and stop function. The one that you see in the middle, it also has a stop function where you can push the button down and then just release and it will stop. There's also a keyed override switch, where typically that is used within schools, especially gymnasiums, where the janitor or the maintenance crew has a key to turn and open or close the actuator or the operable windows. We also have the indoor sensor for CO2 temperature and humidity. These are as simple as just put it next to a window and it should communicate back. Typically, it should always communicate back. Sometimes you don't get the exact readings depending on the placement of those sensors. And just like the temperature sensor, we have the weather station and rain sensor down to the left. And that is really recommended to be on away from the edge of a roof or on top of the roof, so that it can take in the full outdoor environment. And again, we have the cloud-based, which would be with the dongle system, the USB stick. You can take that, and we do have a system where it's a cloud-based, where we have an app that can be put in depending on the manufacturer of these systems, to where you can have control through your phone or through an iPad. So maybe a teacher has an iPad in a school, or the sales director has a keypad or an iPad to control the entire office. And with that, that is all of the products and integration. I'm sure there's integration questions which we can jump into later. So I will throw it back to Casper.
Yeah, so it's close to question time, but I will just quickly present 2 examples of the strategies that we use during the shoulder seasons and potentially the winter time. Because what I talked about before with night cooling and air movement and so on is to increase comfort when it gets warmer outside. But the window operation itself gets really important during the shoulder season. And so what we can see here are the concepts I talked about before with pulse ventilation and trickle ventilation. And they're used in combination here to maintain a good indoor air quality throughout the day. So you can see this is a more extreme example of automated control, where you have a lot of pulses throughout the workday, and trickle ventilation when the pulses are not sufficient in terms of the air quality. But we also have more simple approaches. It's also possible to create a schedule for these pulses instead of having them happening purely demand-based. And the great benefit of this is, of course, back to the psychological effect for the building users, is that they will know exactly when these pulses are going to, when these window openings are going to happen. You can define these in different ways, so you can have window openings at certain times that always happens, and you can have some that will happen at that time if the sensor reading of the CO2 concentration is above the threshold. Now, in reality, we will most likely see some combination in between the more extreme case of automated automation or automated operation and these scheduled pulses. And of course, this will also be combined with the manual override of the occupants, so they always have the feeling of control of the environment that they stay in. And I think with that, we will move on to the question time. I think that's all from me and Michael. Right, Michael? Do you have anything more?
That was all I had.
That's good.
Great. Thank you, everyone. We have time for a few questions. I'm going to go through the Q&A window. There's a question from Charles. Regarding manipulating ASHRAE comfortable zones, what can be done on hot, humid days, say 78 °F and 50% humidity and higher?
Yeah, there is the radiant temperature with night cooling or slab systems and air movement. But in terms of the humidity, there's not a lot that can be done except in House Zero, the project I showed before. They actually use hygroscopic materials in the building that can help absorb some of the moisture in the air. But there's not really, or it is limited what can be done with natural ventilation for operable window, and that's where we see a lot of the projects being mixed mode, where you can really take advantage of both the best of both worlds, where you have natural ventilation when it makes sense, and then have the possibility for a mechanical system in the times where it's not possible to use the operable windows, depending on the location.
What actuators would you use for a parallel opening vent?
So those could be, those are typically chain actuators. There's a great project the Bullitt Center in Seattle, Washington. If you go on our website, we have a couple project reference pages, and that shows that we have 2 chain actuators on each side of the window to help push that out. And they have the, I can't think of the word on the hinges, but they're kind of the, not accordion, but that might be right too. But they have the more accordion hinges to it, so where it pushes it out and comes back in. But you can really use any chain actuator on parallel pop-out windows.
Cool.
Any size, I should say.
What is the average premium cost per window for supplying and installing actuators?
Ooh, that's a great question. I would have to look into that. I don't really know that answer. Unless Casper does.
No, I'm sorry, I cannot. It depends a lot
Yeah.
on the manufacturer and
Yeah.
window type and so on.
And I just did get a note from Jason in the chat that it's scissor hinge. That's what I was trying to figure out. So scissor hinge is for the parallel pop-outs.
Yeah.
We have time for one last question. Are the motor controllers able to be programmed so that it can be overridden by a fire alarm system when it turns on, where the automated window vents can be opened if they form part of a smoke control system in the building?
Yes, they can. They can be integrated into a fire smoke or fire safety system where if the alarm goes off, the windows will operate accordingly.
Okay.
And that's usually done between the BMS system and the fire safety people, and then in coordination with the actuator provider to coordinate that from our control panel to their control panel.
Okay, we have time for a few more. Is it recommendable to retrofit windows with actuator?
I've seen projects where it is. We actually have one right now that we're working on where the actuator is retrofit with the window.
That it's very common. We've Window Master has been around for 30 years, and we have a lot of projects with that's retrofitted. Also historical projects where you have to be very mindful of the aesthetics.
What are some good ways to naturally ventilate high humidity climates like New Orleans?
Yeah, again,
That would be mixed mode, right, Casper?
yeah, humidity, when it gets very high, humidity is an issue. It depends, again, it's a conversation. It depends what is acceptable of the occupants, but it will often end of course, in a mixed mode system where you can use the mechanical ventilation when the operable windows is not possible. But I will say in these mixed mode ventilation, we often see that it ends with the natural ventilation being used more than what was anticipated during the design process and the simulations and so on, based on the feedback of the users. And this is back to this concept of being more accepting of more extreme conditions when you have some control of your environment.
Okay, well, that brings us to 2 o'clock. I'm going to give some closing words. Thank you all so much for attending the live webinar, Enhancing Indoor Environments with Mixed Mode Ventilation, a CE Strong webinar series powered by the Architects newspaper. This presentation was sponsored by Window Master. This webinar is recorded and can be easily replayed using the same registration link. Please allow 7 business days to process certificates of participation and AIA credit reporting for this presentation. A big thank you again to our presenters Michael Sullivan and Casper Holmark-Raven, and to Window Master for sponsoring this webinar. We hope to see you all again at a future event. Have a great day.